test is next Tuesday, and I really just intend to review. There were some things I wanted to add, but I think we need to at least do the chapter on molecules before I back up. But it was these first three that I skipped at the very beginning of class. They just make so much more sense after you see molecules. But, so, this is what you had. So you had a question on density, and you asked about making formulas. So let's do that. And we'll see. Compounds. When you practice, were you using the quizzes?
I looked at the book and the quizzes, but I just keep getting confused with how to know what numbers to put down.
Do you think there's specific questions that I should go over, or just do it in general?
Just in general.
I guess we'll do these. Problem 3.14. Sodium. You look on the periodic table, you can see Na. Periodic table I use, and you'll also have for the test sheet polyatomic ions. So here's bicarbonate. HCO3. Does the polyatomic ions confuse you?
No, it's more so like making it balance.
Okay. So you find out, so the question asks, you have sodium and bicarbonate. Write the formula. So for bicarbonate, you're going to look here, find bicarbonate. Here you get the whole formula for bicarbonate and its charge and its name. And sodium, you would go here. There's sodium. And you get the charge from sodium by looking here. So what's the charge on sodium?
1
So those are the two ions I have to bring together and make a compound. They balance as is. Does that make sense? So you could just write the formula. That's easy. Potassium and nitrate. These are all, okay, nitrate, NO3, and the charge is negative. These are all too easy. So charge on potassium, potassium is here. So this one is easy too. So they just balance as is.
Maybe I'm getting confused with like the O3. Like like I'm looking at the wrong.
This,
Yeah,
that's why these will confuse you. The NO3 is just thinking of it as one unit together. Maybe I'll do better if I just make some up. What if you had, calcium nitrate? So this is nitrate. And what's the charge on calcium? +2, so if we had that, Ca2+. All right, and this is what's confusing you. You're gonna need 2 nitrates, right? To make this balance. Does that make sense?
yes.
The way you would write that, Ca, NO3, 2, parentheses. If you're gonna use more than one, that's when you use the parentheses. And this refers to how many of these are present. Does that make sense?
But you don't have to put the plus and the minus again.
No. Once these are put together, they're neutral, and there's no charges. I mean, technically, this is 2 plus, and this is 1 minus. But once you write the formula, you don't need to write the charges. So I've got these separate out like this, so I wrote the charges. But when I brought them together, everything's neutral. I mean, they are still technically charged, we just don't write the charge. You want more of those. Polyatomic ions. I want to make sure and do this. Okay, bromide. So which atom are we talking about for bromide? It's bromine. And it's here. Br. And what's the charge on it? So -1. Ferric I have on here. Don't I? Yeah. Okay, ferric. So that's Fe3 plus. So to make this balance, I need 3 of these. Makes sense. So I would go Fe. Makes sense. I do think the confusion generally comes from the polyatomic ions. What else do I have here? Chromium 2 chloride. Chloride is Cl. What's the charge on Cl? That's going to be -1. Chromium, Cr, what's the charge on chromium? Chromium is on the periodic table, it's down here. Because it's one of the transition metals, or one of these, it can have more than one charge. So how do you know the charge on chromium? That tells you the charge on chromium. So it's 2 plus, so I need 2 chlorines to make it balance. That's the formula.
How do you tell when I put like the numbers of chromosomes?
How do you tell this?
How do you like, when you write that, how do you decipher when to put
You have to be told somehow what the charge is. Like these have definite charges. There's no way around it. These are +1, these are +2, and aluminum is +3. All the other ones you have to be told. I don't make you memorize these.
So
But-
you only put the Roman numerals when you write out the full name. When we don't know the charge, or when the charge is given, or when
When,
it's transitioned?
when it's one of these or one of these, there will always be that parentheses. Because the reader of this has to know what the charge is.
So just on the transition.
Just on transition metals plus these. I don't know what they call these. P-block metals, maybe you could call these. But you're not, so in this case, you were given this. This is what was given, chromium 2 chloride. So that's how you do the charge, I told you. You had to know that to come up with this formula. Another way you might get this is, you're given this, and you're told to come up with the name. You know the back end is chloride. But what if you were just given this, and you look at this, and you go, that's one of those transition metals, and now you're going, well, Embry, how do I know the charge on this? You infer the charge because you know the charge on this. So sometimes you have to infer that. So when I tell you, you have to be told somehow. This is what I mean by somehow. You might have to kind of go indirectly, but you infer it for it to be a fair question. So you look at chlorine, and you go, it's -1, so I've got a total of 2 negative charges here. And there's only one chromium here, so all of the negative charges on this one atom. So that has to be, or I could write it like this. We've got a Cl negative and a Cl negative. We've got 2 of them. So we've got a total of 2 negative charges. And then we've got 1 chromium. So all of the positive charge for the chromium has to be on that 1 chromium, so it has to be 2 plus. And that's where that's coming from. So you're either flat out told the charge or you infer the charge from the formula. When I did this the other day, I think I confused some of you, or I just think it's confusing. What am I thinking here? Something. What if you had? And you were asked for the name. One of the things you have to do is titanium's down here. One of the things you know you have to do is figure out the charge on titanium because it's going to need a parentheses. But you could. So what's the charge on oxygen? -2. It's right here. So 1, 2, and we've got 4 of them. We've got just to diagram it out. We've got 4 of those. That's a total of 8 negative, right? And we've got 2 titaniums, and those have to add up to 8 plus. So you split that 8 plus charge among 2 titaniums. So in this case, we're inferring the charge, but we're having to split the charge among 2 different titaniums. So if that one's +4 and that one's +4, that'll add up to +8, which tells you you have titanium 4 because of this. It's not titanium 8. Each titanium there is bringing along +4. Makes sense? So you were inferring the charge, but sometimes you have to split the total positive charge that you've inferred among more than one. But you do split it up. Does that make sense? Does this help? Do you want to look at any specific ones that you're looking at?
No, I think, I kind of understand. I was looking at the bottom numbers wrong. Like getting confused with which one was the charge and which one was the
Oh,
number.
okay. Yeah, when you write the formula, when you write that, there are no charges to be seen. Technically, the charges are still there. I mean, you have these in a unit, and in the ion compound and they're still charged. I'd say go over them some more because we'll review again Thursday if you're still lost. Density.
Yes, please.
Let's look at where did I put density? Any specific one?
Question 6, please.
Let's see. So density of the urine is 1.02 grams per milliliter. Okay. So the information you have is 1.02 grams per milliliter. And I always tell you, go ahead and turn that into, do the math. If 1250 milliliters, you're also given how many significant figures is that? What is it? It's 3. If it was written like this, that period tells you that that 0 is significant, so that's 4 significant figures. When it's written like this without the decimal, then you ignore the zeros in front of the decimal, and that's 3 significant figures. So this is 3 significant figures, and that's 3. That, the way I've written it, that should be the answer. Is that how you did it?
I think that I'm gonna work it out and see.
So milliliters cancel and you end up in grams, and now you're just 1.02 times 1250. Calculator gives me that. But I'm only keeping 3 significant figures. The 5 will round up to 7. So that should be the right answer. Is that the right answer?
It told me the right was 1.28
All right.
kilograms.
Both of them are correct,
Okay. Oh, that makes sense.
which is still a problem with the answer key. If this specified kilograms, then you could answer it. Yeah, let me look at it. Kilograms, 1,000 grams. No. That wasn't right. I did that wrong. Did you catch me? Sorry. 1,275 grams. If I'm rounding that, it's actually that. I have to put a 0 there. Does that make sense? Let me do this again. If I do 1.02 times 1250, I get this. I could put a decimal there, it really doesn't matter because there's not a 0 to deal with. But I can't say 128. The answer is I'm keeping 3 significant figures. The 5 rounds up to 7. that has to be a 0 there to locate the decimal. That's what it is. So that kilograms is the only correct answer there. That's at 128 grams, not 1,280.
Okay. So for the grams per milliliter, if you're given the density, you can always set it up as that, like
Yeah,
the number will go with the grams always?
yes.
Okay,
When you see something written like this, the numerical value goes with this thing that's first.
okay,
And then the thing that's on the bottom, you just stick a magic 1 on, and then you're set up to do the math the way I do it.
perfect, thank you.
Like if you said 66 miles per hour, that means 66 miles in 1 hour.
Perfect, and then the second value you set up as like what you need to cancel. So you put
Yeah.
milliliters on the top, or is that need to cancel?
You could be given a question like this, where you're given density. Think about it like this, you've got, some number, I'll do it in grams per milliliter. And after you punch in that number and divide by that number, you'll have that. This is the density, this is a number of grams, and this is milliliters. Think of it as, there's 3 different values here, and you have to be given 2 out of 3 to solve any problem. You might be given grams. And then it asks. You might be given these 2 things and asked for the density. You might be given grams. You might be given grams and grams per milliliter and asked for milliliters. 3 different ways to ask this question. So you might be given these 2 things and asked to come up with this. You might be given these 2 things and asked to come up with this. You might be given these 2 things and asked to come up with this, which is how this one was. But if you're given, and then this one was 1250. You're given the density and some milliliters. So in that case, you're gonna go if you were given density and instead of milliliters, you were given grams, let's say, then you would go 2 grams. Now you want to, instead of doing this, you want to take that and flip it over. So I would have 1 milliliter. Does that make sense?
Yes, sir, thank you.
And then you might just be given, 1,250 milliliters. It has 0.932 grams. And then you would just go, to have density, you need grams per milliliter. And then I would just divide this by this.
So even when you flip it, the value stays with that grams because it was the first thing in the
Yes.
fraction. Okay,
It's low density. So yeah, when you flip it, you keep the numbers with the unit. You just flip them together. So if you have a problem where there's only one factor, like this density, and then some number to deal with, there's 3 different ways to ask these. And you flip accordingly, or you just set it up and calculate. So yeah, 1.28 kilograms was definitely the correct answer. The 128 I wrote first was wrong. So just to review some more of this numerical stuff. Let's do these. How many significant figures are here? 3. If the decimal wasn't there, 2. So we do play that game with the decimal when there's zeros just to the left of the decimal. Sometimes they're significant, sometimes they're not. They're just written here, located where the decimal is. Like you might wonder why I would write 160 like that, even if if I know this is not a significant digit, why would I write that? Well, I have to put that 0 there just to tell the reader where the decimal is. That's where the twist comes. So if I want all 3 of these to be significant, I do that. And if it's only the non-zero numbers, I have to do that. How many significant figures here? It's 4. So now that we're beyond the decimal, the writer of this number put that 0 there because it's significant. They wouldn't have put it there if it wasn't. So that makes all of it. So significant figures are always contiguous. So if the writer of this number puts a 0 after the decimal at the end, it's significant, and any non-zero digit is significant. So that just makes all of them significant. What about here? That's 2. So let me reiterate. If there were never any zeros in any numbers that you ever write down, then significant figures is never confusing. It's just all the non-zero digits you write. And usually when you write a number down, that's what you write. You write down the significant digits that are non-zero. It's when there are zeros. So there's this. I was just going to rewrite this one as an example. 3 zeros. So there's that, and then there's this. So there's leading zeros, and there's trailing zeros. Trailing meaning on the other side of the decimal, trailing. Leading zeros, these never count. Those never count. Here's another one with leading zeros. But we almost never write those. When it's on that side of the decimal, we almost never write any of these. But technically, there's an infinite number of zeros out to the left. Those never count. Leading zeros don't count, and this includes crossing the decimal and hitting more zeros. These are leading zeros in both of those cases, and those never count. Trailing zeros, and let's say trailing on the right side of the decimal. Here's a different number. Both of those are trailing zeros on the right side of the decimal. Those do count. The writer of the number wouldn't have put it there if it didn't count. Again, there's technically an infinite number of zeros going out to the right. But the writer of that number included that one, so it counts. The other weird thing is when you have this situation. Let's say I calculated a number, and that's a number 440. But but really I only mean to express two significant figures. So the only way to do that is this convention with the decimal there or not. If I mean two significant figures here, then I don't put a decimal there. And if I do mean everything all the way up to the decimal is significant. So this is two significant figures, this is three significant figures. So there's the leading zeros, there's 1 0 rule to deal with. Trailing zeros on the other side of the decimal. And then there's this deal where you just so happen to have an answer where there's a 0 here just before the decimal. And you have to decide how to write it because of your significant figures. There's also, what if I did a calculation and I landed on 4,400? How am I going to write that? Well, if you mean to write down two significant figures, you don't put the decimal there. But if you did your input values, the lowest number of significant figures is 4, then your answer needs to be in 4. And if you just so happen to land on a couple of zeros right there, just before the decimal, you can tell the reader of the number how many significant figures, if it's actually 4. The difficult thing is, so I would include all those with 3. The weird one, the weirdest one, the most difficult one to deal with is, let's say, I calculated my answer, that's 2,500, and only 3 of those are significant. There's no way to do that with this cute little decimal or not. That has to be written in scientific notation, there's no way around it. If I don't put a decimal there, it says 2. Let's say it needs to be 3 significant figures, because I did the calculation and I know what I'm trying to write down. But I can't represent 3 significant figures like that. That shows 2. If I did that, that shows 4. So the only way to do that is scientific notation. You run into that sometimes. That's the only way to write that number while simultaneously expressing 3 significant figures. And when you do in scientific notation, literally represent the 3 significant figures right there. When you see something in scientific notation, you can literally just count the digits, including the zeros. Like these, that's necessarily 4 significant figures, that's necessarily 2, because of the way it's written. Let's do round these to 3 significant figures. It's 3, right? Round these to 3 significant figures. So this is 25,401. There's my 3 significant figures. The 0 does not round the 4 up, so 2, 5, 4, and I have to put zeros there. And I want to leave it like that because I'm rounding this to 3 significant figures. That's in the instruction. If I put a decimal here, the reader of this number would see 5 significant figures. So that's that one correct. Rounding this one to 3 significant figures. It's those 3. The 8 does round the 4 up, so I have to go 1, 2, 5, and now I'll fill in zeros to locate the decimal. But I'm not going to put the decimal there because that needs to be 3 significant figures. Oh, 1, 2, 6, 5. 0012. Okay. So leading zeros don't count. There's three significant figures. The 5 rounds up to 6. I do that to locate the decimal, and it's fine. That shows three significant figures. If I wanted scientific notation, it would be 1.27. So that converted to scientific notation is this.
Would you put zeros at the end?
Zeros here?
Yeah.
The reason I don't is because this has to be three significant figures. I'm the writer of this number now. If I put zeros after there, I'm indicating that those are significant. You're right to think, now that you rounded this, Embry, now there's zeros out here. That's true, but I'm making them significant if I write them. So, trailing zeros. There are no trailing zeros. If you had this, if you're looking at that and it says round this to three significant figures, those 3, the 5 rounds the 9 up, but that basically takes 29 to 30. I'd have to write it like that. Then I would include a 0 because I meant for there to be 3 significant figures there. Does that make sense? All right, let's do some of these. Multiplication division rule, and there's the addition subtraction. Multiplication division deals with significant figures. Addition subtraction deals with how many after the decimal. So 53.6 times so how many significant figures are here? That's 3. And how many here? 2. That's part of the leading zeros. So our answer needs to be the 2, the lowest number. My calculator gives me, and now I'm going to take that and round it back to 2 significant figures, to those. And 9 rounds up to 1, and that's it. Answer to that question is 22. Addition, subtraction, so 25.825 minus 3.86 I'm going to do this in my calculator, but this is saying I have 3 after the decimal. This has 2, so my answer has to have 2 after the decimal. It can't have 3, it can't have more than that. It's not 1. So if you do this in your calculator, you'll get my calculator says 21.965. I'm not even really looking over here. I'm just looking there and going, it's 2 after the decimal that I need to keep, which of course, therefore, I'm keeping all the way up to here. The 5 does round to 6. And that's the answer. Addition subtraction rule, you deal with what's after the decimal. It's not the overall. This is overall 5 significant figures. This is overall 3. but I never mentioned anything about significant figures. I only talked about what was after the decimal, because it's addition, subtraction. Scientific notation. So for these, for scientific notation, you're looking at the number as written and noting the significant figures there. 1, 2, 3, 4. So how many significant figures? There's 4, so there need to be 4 once we put it in scientific notation. Times 10 to the 1, 2, 3. So that shows 4 significant figures, and the 10 to the 3 scales it back up to this. This 0, 0, 0, 0, 1, 6, 2. So you look at it, how many significant figures are there? It's these 3, so times 10 to the negative 5. So there's the standard way of writing a number. There it is in scientific notation, and you see the 3 significant figures. Any more of these you want to do? Now we're converting from scientific notation to the standard form. .4 times 10 to the 8. So the standard form here is, I'll just do it like this, 3.4. 1, 2, 3, 4, 5, 6, 7, 8. So there's the standard form. $340 million. If you look up here, how many significant figures are there? So written this way is correct. If I did that, I just suddenly made all those significant, all those zeros. So the correct way to write this is like that, without the decimal there. That shows 2 significant figures, 340 million. .822 times 10, negative 5. So the decimals here, and negative 5 is 1, 2, 3, 4, 5. That's where my decimal goes. I usually write this 0 as well, so 0. This is showing 4 significant figures, that's showing 4 significant figures. Leading zeros don't count. You guys good? All right, 1.69. So cholesterol concentration here in blood is 186 milligrams per deciliter. Convert this quantity to grams per deciliter. So the information you've got for A here, you're told 186 milligrams per deciliter. milligrams. Milligrams per deciliter. And you're asked to put it in grams per deciliter. The question is grams per deciliter. And like I said before, write down 186 milligrams of 1 deciliter. We have to put something here and then equal. We need to end on grams per deciliter. Another way of saying some number of grams per 1 deciliter. So I need some numerical value here. Deciliter is the same, so we don't need to cancel that. We need to cancel milligrams to grams. So if you fill that much in, you can see that the milligrams cancels and you end up with grams on top and deciliters on the bottom. How many grams are in or how many milligrams are in a gram? And up there. So I'm going to give you this on the test. That one's probably down in this list. One gram is 1,000 milligrams. 1 gram. So basically 186 divided by 1,000. And my calculator gives me probably what the answer says in the answer key. So actually, I have 4 numerical values here. And I didn't include the ones, but basically the math I did was yeah, I just grabbed my calculator and divided 186 by 1,000. But rules about significant figures, multiplication, division. This 1 on the bottom, whenever you see something like that, the 1 on the bottom that you put on the bottom for the DL, that's always exact. And metric to metric, those are always exact. That's why I didn't look at this and go, 4 significant figures or 1 significant figure or any of these. I really ignored those for significant figures. I got all my significant figures here. Metric to metric, it's always exact number on top, exact number on bottom. English to English or standard to standard, whatever you want to call it, like 4 quarts to a gallon. So metric to metric, top and bottom are exact. English to English or standard to standard, whatever it's called, those are also exact. It's when you go from English to metric that one of those 2 numbers is not exact. One of the numbers will be a 1, the other number will be a non-1. The non-1 gives you some significant figures to deal with. It's these metric to English. So these are all showing you metric to metric. I mean, for this 1 kilometer is 1,000 meters, you would write and that's exact because it's just metric. It's stuff like this goes metrics to standard or metric to English, however you want to call it. In this case, that's exact and you have 3 significant figures. figures. This is showing the conversion from English to metric to 3 significant figures. Something like this, 1 kilometer equals 0.621 miles. That could be made more accurate. There's more digits out here. Whoever wrote this little table here just made them all 3 significant figures, but they could have made it more. All right. All right, patient, so a lot of this is reading comprehension. They make them sound more complicated than they are. I tend to keep it as simple as I can on the test. Underactive thyrogram, 88.0 micrograms of this medicine. How many, okay, each day, how many milligrams of this medicine do they take per day? So for this one, we would, to formally set it up. So I will expect to see some of your math, at least some math for your questions on the test. Was it 88? Microgram. We need to go from micrograms to what is it? Milligrams, yes. How many micrograms is in 1 milligram? I don't think that's in here. Yeah, they got it, okay. 1 milligram is 1,000 micrograms. 1 milligram is 1,000 micrograms. That's how you'd set it up. The micrograms cancel, you get to milligrams. All right, is that correct? I left a mistake in there. It's not. What's the problem? Yeah, significant figures. This is exact. Whenever I put it over 1 like that with no units, that's always exact. Metric to metric, those are exact. This shows 3 significant figures. This only shows 2 significant figures. To write this correctly, I have to include that 0. Micrograms. Oh, I did the units wrong too, so there were 2 things wrong. The micrograms canceled, it just should have ended in milligrams. So that's correct, 3 significant figures. Challenge rules. So I'm looking at 1.82. Children typically receive a dose of 10 milligrams per kilogram 3 times a day for 7 days. The most formal way to do that one. One 10 decimal milligrams per kilogram. That's milligrams per kilogram of the patient. 3 times a day for 7 days. formal way to set this up. They purposely put more information in these than you really need. Oh no. How many grams? 28 kilogram child. .28 kilogram child, taking 10 milligrams per kilogram. And what we do here. Yeah, I think the best thing to do here is just go. Do that and then multiply by 14 or 21. Does that make sense? 3 per day for 7 days, that's 21. I have to really play games with these units to make it all cancel. Per kilogram per day. This is just more complicated than I would put on a test, but all right. These are exact. 7 days exactly, 3 doses in 1 day exactly. This is 2 significant figures, this is 2 significant figures. That's exact. I'm not going to get the answer to this one. I'm doubting myself here. So that's how many kilograms per dose. And then we multiply this by 14. So 2 significant figures, 2 significant figures. I'm expressing 2 here, right? So 280 kilograms. So the kilograms cancel. 280 milligrams per dose times 14. Probably shouldn't have done this one. So how many milligrams? Just move on. How many grams would a 20? So I'd still have to convert this to grams. That was, that one is just too much. It's not that hard, but it's more than I would put on a test. I guess I shouldn't have gone to the challenge problems. We've got 15 minutes. What should we do? Let's look at these. I didn't put any of those temperature conversions on here. So this first one, you've got 3 after the decimal here and 1 after the decimal. So your answer has to have 1 after the decimal. So this can't be the right answer, this can't be the right answer, this can't be the right answer. It's gonna be one of these two. You can tell that just from looking at it, right? $38.251 plus 73.1. And my calculator says
So I'm keeping that decimal, 1 after the decimal, and of course the rest of it. But the 5 rounds the 3 up, so the answer here is that. You follow that? You guys okay with these?
Maybe we should, start reviewing. Start reviewing chapter 2. Outermost electrons, those are the valence electrons. Halogen in period 3, so where are the halogens on here? Group 17, aka 7A. I only named 3 groups here. The one on the far left, not counting hydrogen. You remember what those are called? Alkali metals, and the next one over are called alkaline earth metals. These are the halogens, and these are the noble gases. Textbooks just love those 3. All the groups have names, but they just love to do those 3. Where was I? Oh, halogen in period 3. So the rows are periods, so this is period 1, it's just hydrogen and helium. Period 2 is lithium, beryllium, boron, carbon, so there's period 2. Here's period 3, and there's the halogen in period 3, fluorine. What else should we do? Any one orbital can hold a maximum of how many electrons? Let me remind you of this. The way I do the orbitals, my Christmas tree model, you got 1, 1, 3, 1, 3, 5. When you draw these, it helps to line them up. I didn't quite do it. The 3, I put 1 in the middle and that on either side. The 3, 1 in the middle, that on either side. It just makes it look more symmetrical. If you can do that much, you label the single ones S. There's one more 4S right here. That one kind of breaks the pattern, but so that's why I say 1, 1, 3, 1, 3, 5. Just remember there's one more 1 in between this 3 and 5. The ones that have 3 lines are called p orbitals. The ones that have 5 are called d orbitals. D, D, D. And these have numbers now if you start back at the beginning. That's 1s, that's 2s, because I've started with 2's here, then these are 2's. This is 3s, and that makes these 3p's. And these are 3d's. And that pattern that breaks here is because the 4s starts there. If you can just walk up to a piece of paper and do that much, all of this electron configuration stuff just falls into place. So that's why I always teach it this way. If you can do that much, then you can just start filling in electrons to make any of these. But what I was going to say is just a little more vocabulary. This is the first shell. This 1 represents the first shell, so I'll say these 2, I mean this is the second shell. The third shell are these 3, not the 4, but these together comprise I mean the rest of this you can fill in too, if you just remember this. This is also sometimes called the n equals 1 shell, n equals 2. The 4th shell starts here. There is a 4s, and then there's
3 for the P's, and then there's 5 for the 4 D's. But the rest of this you can build from the periodic table. So I just stopped there. Once this pattern breaks down and starts getting weird, then you use the periodic table for the rest. Orbitals, or each individual line on this diagram is one orbital. So how many electrons can one orbital hold? It's 2. How many electrons can the n=2 shell? If it's 2 per orbital, 2, 4, 6, 8. You're gonna get a total of 8 electrons in the n=2 shell. These are called subshells. You could call this the P subshell for n=2. So total electrons that can be in the P subshell of n=2, or the second shell, 2, 4, 6. So it's just a matter of knowing the vocabulary that goes with this diagram to answer those types of questions. They're only tricky because of the vocabulary. Orbitals can hold a maximum of 2. Valence electrons. So let's go ahead and do, I'll just pick one of the halogens. And I'll do chlorine. So if you can draw that diagram, then all you have to do is here and go 17. What does this 17 represent for the chlorine atom? Protons, number of protons in the nucleus. So for the neutral chlorine atom, it will also have 17 electrons. So you can just look there and go, okay, I've got this diagram, I'm doing chlorine, the number is 17. As long as you do this correctly, it's 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's the electron configuration of chlorine. Get this out of the way. And technically, I didn't have to write this or this because it stops there. It just makes things look more messy. So that's one way to represent the electron configurations. Books don't do this anymore. They do it 6 other ways. But another way to represent chlorine here is to go 1s2 because there's 2 electrons. 2s2 next, there's 2 electrons. And then 2p, there's 6 total in there. And then 3s, there's 2 in there. And now we get to 3p and we've got 1, 2, 3, 4, 5. That's the electron configuration of chlorine done a different way, encoded differently. You see that? Up through here, if there were no electrons up here, and I had the S and the P's all full, what is that? If these were empty, and we just stopped there, well, that has what we call the stable octet. The atoms, the neutral atoms that naturally have the stable octet are the noble gases. And period 2, so not helium, not hydrogen and helium, but one down all the way across to here, that's neon. You have the 1s, the 2s, the 2p full, and if we stopped there, this is where we would be. That's the electron configuration of neon, if those weren't up there. And this is why they're the stable, the noble gases don't tend to react. They don't tend to gain or lose electrons, and they don't have any unpaired electrons for covalent compounds. But what I want to say here is the 1s, 2s, 2p full, we can do this. We can go electron configuration of neon plus a little more. There's a third way to represent, called the summary way or something. What is that called?